All right, everybody, this is Chapter 1, Functions, and Section 1.1, Day 1, which is on relations and functions. There's some basic definitions I'm going to run through for you here. So first of all, definition of a relation is a set of ordered pairs. So it's showing the relationship between x and y. So when we're thinking about relations, lots of different ways to show those, and we'll talk about that in a little bit. But just a whole bunch of x and y pairs that show a relationship between x and y. So it could be profit and cost, it could be time and population, whatever that might be, we have that relationship. Domain, if you remember from back in algebra, is the set of x values, which I will also say input for. It's what you put into the equation, which could also be then what we call our independent variable. So independent meaning we have choice over that, we're substituting that into the equation. The range then is the y values, which is the output. So if domain is input, then y would be output. And so we call that the dependent variable. So what we have for y depends on what we put in for x, right? So that changes depending on what those x values are. So domain, D comes before R, X comes before Y. Think alphabetical, so domain and range. Okay, there's 4 different ways you can represent a relation. And these are just the different ways visually we can see one on that set of ordered pairs. So one is just a table. You guys have done these a lot. These X, Y ordered pairs that we use to help show a relationship. Usually when we're getting ready to make a graph, we'll have an X, Y table like that, which is really handy. Just a way to show the relationship. A set of ordered pairs. Sets are groupings of things, like a set of luggage, a set of dishes, a set of keys, a set of golf clubs. They belong together. So to show sets, we use the brace, and then we just write out that list showing all the points. So a set, we can think of it just like a list in this case. So think of a set of ordered pairs just as the list of them with the braces. Graph is just making a quick sketch. So you guys are familiar with that. So usually when we are talking about going through and doing a picture like this, we graph those points so we can show the relationship. So we have those points. So a graph is a real visual way of seeing what that picture looks like. And then the last thing is the rule or the equation. So that's being able to express it as an equation or a rule. We'll be working with those a lot too. So if you look at the x's and y's here, how do we go from x to y? Well, how do you go from a -2 to a 2, or a 1 to a 5, or a 2 to a 6? Well, it looks like all the y values are 4 bigger. So if you take the x value and add 4, that would be your y. So that would be the equation or the rule. And that relationship, if you look at the equation, is definitely a linear one. So when you look at where the points are. So we have lots of different kinds of relations. This one just happens to be linear. Okay, speaking of special kinds of relations, the most important one that we're going to be looking at is a relation that's called a function. So I know you've heard of that term before, but let's talk about what functions really are. So a function is a relation. So that's really important. It is a set of ordered pairs. And then we get this really fancy definition in which each element of the domain. Domain, what does domain mean? Well, that's x. So each x is paired with exactly one element in the range. So element in the range just means what is range? That's y. So each x is paired with exactly one y. So for every x value you have, so for every x is paired with exactly one y. Another way to say that is that no x values repeat. Some people prefer that because that means the same thing. If you don't have any repetitions in your x list, that means every x is going to have its own unique pairing. So it's just one x value paired up with the y. So you can't have x values repeat to be a function. They're all relations, but just not that special kind of function. All right, so let's take a look at this example. So it says state the domain and the range. I'm just going to use D and R. They're sets. So the domain would be the set of all the x values. So that's 1, 2, 3, 4, and 5. The range would be all the y values. 1, 4, 9, 16, and 25. So first part is it a function? Well, yeah, every x has exactly one y. 1 is only paired with 1. 2 is only paired with 4. There's no repetitions on your x list. They're all happening just once. So yes, that is a function. And just because we can, let's see if we can figure out what the rule is. To get from the x's to the y's, what's happening to each of those? How do you get from a 1 to a 1, a 2 to a 4, a 3 to a 9? Looks like we are squaring every time. So that's our family of parabolas that we'll be dealing a lot with. So it is a function because for every x, there's exactly one y. So that's from the list, the set of ordered pairs perspective. Let's look at tables. Can you tell from a table? So there's the top and the bottom. Which one represents a function? Well, let's look at the top one. Take a look right here. I see some repeating x values. 3 is paired with 5, and 3 is paired with 9. That means there's 2 different outputs for that one input. That means it's not a function because there are repeats. Now look at the bottom. All of those x values happen only once, so this one would be a function. Now what bothers people is that all the y values are the same. Well, think about what that would be if you graphed it. 2, 3, 7, 3, 12, 3, negative 4, 3. You'd end up with a horizontal line, which is definitely a function. So all the y's can repeat, the x's can't, so that would be a function. Let's take a look at the graph approach here. So there's 2 graphs on your note sheet here. Which one of these would represent a function? For every x, there's exactly one y. Well, for the line, for any x value that you happen to pick, there's only one point on the graph for those, so I would say the line is definitely a function. When you look at the circle, though, pick a value for x, so let's just say x is 0, you have a point on the top of the circle and the bottom. That means for that value of x, you have 2 different values of y. So we would have that happening anywhere you looked on that circle. So this one would not be. Okay, so let's talk about the line for a second again. So are all lines functions? Well, every slanted line would be, every horizontal line would be, but how about vertical? Would a vertical line be a function? Well, at this particular x value, you'd have infinitely many y values, so it wouldn't be. So all lines are functions except for vertical. All right, let's talk about circles. How can you tell just by looking at this picture that it's not a function? And a lot of people are kind of looking down here already maybe to be able to tell that. You guys talked about this last year. If you pass a vertical line across your graph, so a vertical line here, a vertical line here, a vertical line here, at any point on the graph, when you pass a vertical line across, it can only touch at most one point. That's standing for that one output. For every x, there's exactly one y. So if it's only touching one point, like it would over here for the line, we'd be just fine. But when you do that for a circle, it touches 2, one on the top and one on the bottom. So the vertical line says it can only touch one point as you pass a vertical line across the graph to be a function. So when you're looking at those pictures, it's a pretty easy, just kind of scan across and see how many points does it touch. It can only touch one to be a function. All right. Last thing that we're going to do for this first part is function notation for this part 1. Function notation is the way to write the rule. So if you're going to write the actual equation of the function, it's read f of x. So that's this part right here. It is not multiplication. A lot of people see the parentheses and they assume times. It is not multiply. It just means the name of the function is f. The letter you're going to use or the variable you're going to use to write the rule is the x. Those can be different. They don't have to be f and x. It could be function g and the variable is q. It could be pretty much anything. And the way you say it is f of x. So the function f evaluated at x. So basically, then your y is your f of x. It is your output. So when you're looking at f of x, you can think of that as just your answer. That's like your y. It's your output. So when you look at ordered pairs, x comma y translates that into x f of x, because f of x is just like the y. Think of it as your output. All right, well, some of these should be pretty familiar. We'll do the numerical ones first. If you see f of -2, I'm hoping you remember what that means, that your x value is -2. So you're going to do that substitution. You're going to substitute in -2 in for f and do your arithmetic. So be careful when you square. Do you see what I put around the -2? I put parentheses, so when you square it, you get the right sign. So my output then, my f of -2 is 2. Well, that just means my point then, my ordered pair, would be -2, 2. I put in -2, I got out +2. Let's go down and do the other one that has a numeric value. F of 2. That means your x value is 2. So if I want to do f of +2 in this function, remember what those bars mean. That's absolute value. So we'll talk about that. All right, so be careful with your order of operations. Looks like the 4's are going to cancel, so we get absolute value of negative 6. And absolute value, remember, is distance from 0, which would be 6 units. So that means I put in 2, I got out 6. So regular function notation, they're asking you to do a substitution. Now the other two blocks here are asking you to do a non-numerical, not a number substitution, but you can definitely substitute expressions. So we're going to see that a lot in the next section as well. So what they're asking you to put in for this first one is actually m. So the x value is m. So when you do f of m, you are going to replace the x with the m. There's no arithmetic you can do. You don't know what m means. So you're just kind of stuck there until you're given some more information about what m is. So same thing here. Our x is 3a. So you're going to make that substitution. So I'm going to put in 3a and square it, and minus 4. Notice the parentheses again. You're squaring 3a, so that would be 9a squared minus 4. Can't simplify it. I don't know what a is. I can't break it down. You can't take the square root because it's subtracted, not multiplied, so you're kind of stuck there. All right, so I want to finish up last example for this first part, substituting a little bit bigger expression. So a plus 3, that means your x is actually the expression a plus 3, and that's what you're going to plug in. So we're going to plug in a plus 3 into that function for x. So just be careful in your order of operations here. When you square a binomial, multiply it times itself. Order of operations, you'd square first. That means FOIL. So first, outside, inside, last. So be careful when you do that. We're going to write this in descending order. So I want my answer in descending, and hopefully remember what that means. Highest degree term first, which would be a negative a squared. Now just be careful. See how I put the parentheses around that entire trinomial there? That's because this minus sign out front has to be distributed to all three of those terms. So not only is the a squared subtracted, so is the 6a, and it would be minus 9, so minus 9 plus 5 would be a minus 4. So just be careful on that when you look at your arithmetic. That's the biggest issue people run into, is that arithmetic. So we talked about domain, range, relations, and functions, and all the different ways that you can express those. We'll finish up part 2 in the next video, which has to do with domains of functions.